Well, hello. In this video, I am going to go over the perpendicular bisector theorem to solve equations and find side lengths. Let's start off with what a perpendicular bisector is. Now, a perpendicular bisector does two things. It divides the base that it intersects with into two equal parts, and it intersects it at a 90-degree angle. So this line here is doing two things on these triangles, and it's not very clear. This one doesn't look very accurate, but it's not only intersecting at this 90-degree angle, but it's cutting this again base here into two equal parts. So this here would be again congruent. Those two sides would be congruent. Now, while perpendicular bisectors again exist on any triangle, we're going to be focusing on isosceles triangles and looking at that relationship, at that specific type of triangle cut by a perpendicular bisector. And you'll notice that when we have a perpendicular bisector on an isosceles triangle, you'll notice that if again this bisector, if this line is perpendicular, as you see here, to this base here, this line of CD is perpendicular to this base here, and it intersects it into two equal parts, because this is an isosceles triangle, because it does this, this again confirms that we have an isosceles triangle. So the distance from A to C is going to equal to, or better said, that this segment AC is going to be congruent to the segment BC. So it goes into play again, essentially very similar to the lesson that we did on isosceles and equilateral triangles, that these two sides would be congruent if we have an isosceles triangle. Just like right here, if that we have a perpendicular bisector that intersects this vertice up there at a 90-degree angle, intersects this vertice and this base here at this 90-degree angle and cuts these two sides into two equal parts, then these two sides are also going to be equal to each other. And again, it works backwards. The converse of this perpendicular bisector theorem states that if we have again these two congruent sides, AC is congruent to CB, and this line again, this vertical line intersects this segment here at 90 degrees, so CD is perpendicular to AB, then that implies that these two sides, these two segments are going to be congruent. So segment AD is congruent to segment DB, which makes it again very easy to set up and solve equations when we're looking at those segments. Other couple of important things to recognize is that again we're ending up essentially creating again or identifying the fact that we have an isosceles triangle. So these two angles are going to be congruent, and this angle here, ACD, is 90 degrees, just like the measurement of angle BDC is also going to be 90 degrees. So let's look at some examples of how we can use again this fact to set equations up. So the first one is going to be very basic on solving an equation for x. So this one just simply requires again to recognize again using the converse of the perpendicular bisector theorem, that if these two again, or using using the perpendicular bisector theorem, I'm getting stuck with my words here, and I'd seen that these two sides are congruent, and this is again a perpendicular bisector, that these two sides on the triangle are going to be congruent. So 7x plus 24 is going to equal to 13x minus 48. So it basically creates again a line of symmetry in a very practical sense, that if I flip this onto this side, or vice versa, flip this onto this side over here, that the two triangles again are going to match out perfectly. They're going to look, again, they're going to go on top of each other. So this side is equal to this, just like this segment is equal to that segment. And then solving this equation just simply requires us to put our usual letters to the left, numbers to the right. So we end up subtracting 13x, subtracting 24, and we have negative 5x. I'm sorry, that's 6. Negative 6x is equal to negative 72. Dividing by negative 6, we get that the value of x is going to equal to positive 12. So x is equal to 12. Looking at our second example, example number 2. Here, same situation. Again, we have this line here that is perpendicular to this segment there. And since these two again are congruent, again we end up again identifying just a basic line of symmetry. So this here is symmetrical to that one, meaning that these two segments are going to be equal to. So just like before, 17x minus 3 is going to equal to 9x plus 13. And again, all we want to do again is just simply solve this equation for x. So with letters to the left and numbers to the right, we end up with 8x is equal to 16. Dividing by x, the value of x is going to equal to 2. Now on the next example, we want to figure out the measurement of our s. So that would be again this distance right there. So in order to figure out how long that is, we first need to figure out the value of x. So just like before, since we have two perpendicular lines, as we see right there, by the 90-degree angle, and this segment is cut into two equal parts, then these two are going to be equal to each other. So 7x minus 22 is equal to 4x plus 5. So with letters to the left and numbers to the right, we get that 3x is equal to 27. Divide by 3, the value of x is equal to 9. Now we plug that value into this x there, and we figure out the length of our s, which is 4 times 9, which is 36, plus 5, so 41. So relatively easy to set up these equations, nothing hard about that. Here we want to figure out the measurement of EG. So E to G again would just be again that measurement here. So we would have to replace the x again with a value to figure out the distance from E to G. Well, again, since these two are congruent and this is at intersecting this base here at 90-degree angles, these two are going to be congruent. So 14x minus 37 is going to equal to 2x plus 11. If you write it the other way, again, does not matter. Again, we're just simply equaling to each other. So with letters to the left and numbers to the right, I end up with positive 12x is equal to 48. We divide by 12 and the value of x is 4. So with the value of x equaling to 4, I can figure out the measurement of E to F by substituting in 4 in for the value of x. So 19. Oh, EG, not EF, sorry. EG. I put the I plugged it in right, I just labeled it wrong. EG is still equal to 19. Alright, so let's move on to our fifth example now. Our fifth example, we now want to figure out the distance from A to B, which is now this entire distance here. So that's going to require us to plug in the value of x into either one of these two segments there, and then just simply double it, because again they're going to be congruent. As you see right here, we have this 90-degree angle, so it's perpendicular, and since these two sides are equal, again that means that this is going to be also be a bisector. So letter D or CD is a bisector, so it's making these two sides congruent. So 5x minus 11 will equal to 3x plus 17. So letters to the left, numbers to the right. 2x is equal to 28. Divide by 2. X is equal to 14. So nothing difficult about there, but since we're figuring out the measurement here from A to D, I only need to plug it into one of these two values. So let's plug it into this one. A to D is 5 times this value of x minus 11. Well, 14 times 5, that's equal to 70, and 70 minus 11, that's equal to 59. So AD is equal to 59, which means that from D to B, that is also going to be 59. No reason to plug it in there. Again, I know that these two segments again are congruent, and D is in the middle, so these two segments are going to be congruent. So also 59. So 59 times 2 is going to give me the distance from A to B. And 59 times 2 is equal to 118. So there's your solution. So this one is pretty much the same thing as what we did on the previous one again, but since we wanted to figure out the entire length of the base on the triangle from one endpoint to the other endpoint on the base of this triangle, that simply required us to add the two segments. And here we are looking for the measurement from J to K. So example number 6 is pretty much the exact same type of example as example number 3. When we're looking again from R to S, here is just J to K. And just like before, these two sides are going to be congruent. So 6x minus 26 is going to equal to 3x plus 34. So with letters to the left and numbers to the right, we get that 3x is equal to 60, and dividing by 3, x is equal to 20. So JK would be 6 times 20 minus 26. Which is equal to 94. And that concludes all our examples. So these examples were a lot easier than other examples that we've done on triangles so far. And I hope again this was helpful and easy to follow. If you haven't again subscribed to my channel, please do so you can get the latest updates and notifications on video uploads. Well, again, thank you for watching. Hope you have a good day.